In this video, we're going to see how we can use similar techniques to before to find point estimates and confidence intervals, but this time we're going to be estimating the parameter that is the population mean. So again, if I want to estimate the average adult male height for everyone in the population, I can use a sample and the techniques in this section to see how we can estimate that. We'd say, here's a point estimate for it, here's a confidence interval for it, and so on. Now, in a lot of previous sections, we've been using the normal distribution over and over and over again, and it's been a very, very useful distribution. It's one of the most commonly used functions in our calculator that we're dealing with in this class. However, it turns out that we're going to use something a little bit different than the normal distribution in this section. And this goes back to a guy named William Gossett. He was doing some studies for the company he worked for, and he was finding that the data, as he was doing these calculations, wasn't quite matching it up with what the normal distribution said it should be. And the situation he was dealing with was things that have small sample size. And when you have a small sample size, right, the central limit theorem doesn't quite kick in. And we don't know the population standard deviation. And what he did was he studied this case and he came up with a new distribution. And if I were to draw the picture for you, at least with my artistry skills, you are not going to be able to tell the difference between this new one and the normal distribution. It's not like they are wildly different. They are pretty similar here. However, it turns out by using this new distribution, you're able to get a little bit more accurate answers. And that was a pretty big breakthrough in what work he was doing. However, you'll notice this is not going to be called the Gossett distribution, even though he was the guy that came up with this, because the company he was working for at the time, they didn't allow him to publish the results because they wanted to trade secrets. And so when he published it anonymous and just called it the student's T-distribution. So that's the name that's kind of stuck, even though, again, we now know who did the work originally. But this is what we have. It's called the student's T-distribution. It is, again, if you were to draw the graph, it is very similar to the normal distribution that we saw before. However, we have a few things here. So properties, it is again going to be symmetric. And by the way, the formula for T is x bar minus mu over S over square root of n. Now, that might look a little bit different than before. Before we had z was x minus mu over sigma. That was the z-score for something. The difference is, remember when you take it as a sample of size n, the standard deviation changes. You have to divide by the square root of n there. And the only difference between that and this one is now we are using the s in the denominator, the sample standard deviation, because once again, the point of these problems is we're trying to estimate something about the population. It would be highly unlikely that you would know the population standard deviation but not know the population mean. And what we're trying to do is we're trying to estimate the population mean. So you should never go into this saying, oh, of course, we're just going to use sigma. We know what sigma is. We're not going to know what sigma is. All you're going to have is the data from the sample you took, and that's what we need to base it off. So it's a symmetric distribution here. However, the graph will change based on the value of n. So if you do T-distribution for n equals 3, then it's pretty much going to be different than if you did the T-distribution for n equals 17. They're not going to be the same graph. Again, it's not like we're talking about graphs that are going to be hugely, hugely different. Maybe one is just a little bit more concentrated in the middle. It's not like the graphs are going to be insanely different. But they are going to change for each n, and that's why n is going to be an important factor in the calculations. Again, our calculator will take that into account for us. And we're actually going to give a name of this called the degrees of freedom. And for these problems, the degrees of freedom is n minus 1. And the reason why is if you have your sample and you know what the average is for your sample, then once you know the first n minus 1 terms, the last one can be calculated based on knowing the average. So for example, if I tell you that I have 3 numbers and I tell you the average of those numbers is 2, well, there's only one possible number that could go in this situation, and it would have to be 3. So the idea is, if you know what the average is, the last number can just be calculated from that, so the degrees of freedom is just n minus 1, one smaller than the data size you have. Another one here, another property, is that as n gets larger, the t-distribution gets closer to the normal distribution. And this is the reason why Gossett was even noticing things, because he had very small n values for his samples. If he had samples of size 100 or 1,000, then it probably wouldn't have noticed it, because at that point in time, it's very, very close to the normal distribution. Regardless, we now know that as you know, there is a different distribution, t-distribution here, and for small values of n, it's more important. So now that we have this idea of this t-distribution, this is the thing that we are going to use to help us build the confidence intervals. Now, let's talk about point estimate before we do that, because we always have to start with the point estimate and then have our margin of error. So let's suppose we take a sample of size n, and we're going to calculate the sample mean and sample standard deviation, x bar and s. And we have to pick a single number to guess for what the population mean is, which is mu. So our best guess for mu would be x bar. So once again, you're trying to guess the population version of the mean. All you have is your sample data. So if you have to pick a single number, we're just going to guess x bar. That's our sample mean. Okay, so that's our point estimate. Now we need our margin of error to find our confidence intervals. And you may remember before, the formula for margin of error in the previous one was z alpha over 2 square root p1 minus p over n, although again this should have been p hats. Right now the margin of error is going to be t alpha over 2, because we're using the t distribution now instead of the normal one. And then for the standard deviation part, it's going to be s over square root of n. So that is our margin of error here. So then our confidence interval, you would go ahead and you would take your sample mean x bar plus or minus the standard t alpha over 2 times the standard deviation over the square root of n. So this is how you're going to find your confidence interval. Now again, we're going to have one example where we do it by hand. However, at that point in time, we're also then going to have a separate video where I show you how to do it in the calculator. So I wouldn't get too hung up on this here. So it says here that we are taking a sample of size n equals 36 individuals, and our sample data gives us an x bar of 35 and an s of 12. I want to find the point estimate and the 95% confidence interval. Well, we already know the point estimate without doing any work is just the x bar value, so in this case it would be 35. Now to make our confidence interval, we need to figure out that t value. And so for 95% confidence, I'm going to look that up in my table, and I have to look at 35 degrees of freedom, because in the table they have a degrees of freedom column that you're looking at. So I go down to 35 degrees of freedom, and I'm going to look up the alpha over 2, so it's going to be 0.025 here. And what I am getting here is 2.030. So that is my T alpha over 2 value here. Now that I have those, I can put it in my formula. X bar plus or minus T alpha over 2 times S over root n. So 35 plus or minus 2.030. S is 12 over the square root of 36. That's 35 plus or minus, I'll do a little bit of calculation here. So that is 12 divided by square root of 36 is 12 divided by 6 is 2. And 2 times 2.030 is 4.06. And if I do the adding and subtracting here, 35 minus 4.06 is 30.94, and 35 plus 4.06 is 39.06, and so this right here will give you your 95% confidence interval for the population mean. Again, this is how you would do it by hand. We will have a next video where we will show you how to take the same problem, put it in your calculator, and spit out the same answer.